right, ladies and gentlemen, we were working on free body diagrams in class, and this was example 4. And I got to example 4 with some of the classes, didn't get there with others, and so we're going to go from there now. So we have mass 1 and mass 2 that are connected with a rope, and we are pulling on them on mass 1. It says that there's no friction. So since there's no friction, what's going to end up happening is, first of all, we can give both of these objects gravitational force. That goes straight down. So we're going to have there for M1, F of G1, and one here for F of G2. Okay, now both of these are on a horizontal table or surface, and they're not falling through that surface, so that must mean that there's a perpendicular force pushing upwards so that they don't fall through, and that's known as the normal force. And because these are not moving up and down, the normal force and the gravitational force should be pretty equal to each other. Okay, and so we'll label F of N1 and F of N2. Then I'm pulling on on mass 1, and I'm pulling to the left. So I would have to put an applied force to the left on mass 1. Well, mass 2 is not getting pulled to the left by that force. What's actually pulling it is the tension. So on mass 2, we're going to put a tensional force. Now, there is a rope between mass 1 and 2, and so if mass 2 is being moved by that tension force, then there also has to be that same tension force on mass 1 because they're connected to the same rope. So that force is going to be the same on both of those objects. Now, since there's no friction, because we were told this was without friction, this would be our entire picture. If there were friction, though, mass 1 would have an additional force vector on the right-hand side with the F of t vector. And then mass 2 would have an additional vector as well going to the right to counteract the motion of these two blocks. All right? So, our next example was a sled, and I kind of got caught on one of my classes with this one. One, I didn't even get to this one, and one, we already did it. So just work with me depending on where we got in each one of my classes. So, I am pulling this sled at an angle, like with a rope that it's at an angle to the ground. And I know the angle is alpha, and I know the force is labeled as F, and that's a resultant force. So that's something we need to think about as well. Again, the very first thing you can do on almost all of your free body diagrams is give it an F of G. Okay, and then because the box and the sled are not falling through the ground and or the sled itself, then there also has to be an F of N value. Now, when you draw a free body diagram, you draw all the forces that are involved. So I would have an angled force right here, and that's an applied force, because I didn't actually say that it was a rope. I just said that there was a force being applied at an angle. So I would draw that force at an angle, well, just like that. Then I was told up here where it says example that this is with friction. So if I'm trying to get the sled to move to the right, then friction is going to go to the left. All right. Now, the thing to realize is with free body diagrams, you never, ever, ever put the components. But what would exist here is since we know this theta right here, and we have an angled value, then we can find an F of a x and an F of a y. So the thing to realize is that if this box and sled are not moving up and down, then the F of AY plus the F of N would have to equal the F of G. So when I'm pulling on something, I'm actually lessening the, when I'm pulling at it on something at an angle, I'm actually lessening the force, because then we would be looking at balanced forces. Balanced forces are just going to keep objects doing what they are doing. Unbalanced forces are going to allow for them to be a change in movement. So if we didn't want this to move up and down, then all the up arrows have to equal all the down arrows. All right? Now, our next one, oh, I'm clicking through blank slides here. I did ask you to do the practice problems that were in your packet for the free body diagrams. So hopefully you did those. If you didn't, now would be a good time to kind of look at those in your packet and kind of sketch these out as we're going. If you haven't done them, if you didn't remember to do them, ask the sub to pause this real quick. Give you about 5-10 minutes. Do as many as you can. Then turn this back on and you can go over them. I know with my 5th period, I'd already given you time, so we'd already started going through these, so you can just keep rolling with this. So for number 1, again, if you need time to pause, just pause it, come back to it. I have a book at rest on the tabletop. So here's my book. It's on the tabletop. So if I'm just going to draw the free body diagram, I'm just going to draw the object, which is just the book. So I'm drawing the book, and the book has gravitational force. It also has a normal force, which should be equal and opposite. Beyond that, I don't have to do anything because it's at rest, so it's not moving. Number 2, a girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. Well, the bar is here, and the bar would have to have 2 ropes going up, and that would be my F of t. Now, the bar also has an F of g value. Then I'm going to have my girl as well, and she's hanging, so she's going to have some F of a's here, because those are kind of applied forces. Her hands or arms aren't really ropes. But she also has an F of g value. So my F of t, my 2 F of t's have to be able to, if she's motionless, then my F of A's and my F of G's have to be equal to each other for the girl. So this would obviously, I guess I could have labeled them, this was F of G1 and this is F of G2, because that's for the girl versus the bar. And the F of A's are with number 2 and the F of T's are with number 1 as a system diagram. But the F of T's going up have to equal all the things going down, as well as the F of A's. So if we had F of A plus F of A plus F of T plus F of T, all those up forces would have to equal all the down forces if everything was going to be motionless. All right. Now on number 3, we just have an egg free falling. So I'll just do a dot because you can do these as dots as well. And it's free falling from a nest. Now, and it says to neglect air resistance. Well, if it's free falling, what do we know about free falling objects? Well, they accelerate. So if they accelerate, then my F of G is all I'm going to have, because that's going to mean that there's no forces stopping that from accelerating. So that's exactly what it's going to do. Okay. Then on number 4, I have a squirrel that's gliding from a tree to the ground. So really it's just going from the tree to the ground, which is vertical. So here's my lovely little box flying squirrel. And he has a weight. So that would be F of G. Now, it says, though, that he's going at a constant velocity. And for it to be a constant velocity, that means there's no change in the motion. It's just going to keep doing what it's doing. So if there's no change in the motion, then the forces have to balance out. So I can't just have this force. It does say to consider air resistance, though, and air resistance is really just a special form of frictional force. So this F of F would have to equal this F of G in order for me to just hit a constant velocity and not change at all, and for it not to be accelerating when it goes downwards. So that would be the picture for number 4. We'll go to number 5 next. Number 5 is a rightward force is applied to a book. So here's my book again. And remember, my book has a weight, and it's not falling through the desk, so that must mean it has a normal force too. And it's got a rightward force applied, and it's accelerating to the right, so that would be the only thing I have. I do have to consider frictional forces, but when I draw this diagram, in order for this to be accelerating to the right, then that means my forces to the left can't be equal to or bigger than this. So when I drew this frictional force, it would be a smaller arrow. Because remember, everything in the x-plane would have to be added or subtracted, vector addition, just like we talked about. So it's different directions, so you'd subtract them. So if we want to have some leftover force that's going to make it accelerate to the right, then we're going to have a bigger force. And that leftover force that's going to get created is called the net force. All right. Now with 6 says a rightward force is applied to a book in order to move it across the desk at a constant velocity. So we're just moving it across the desk again. So we're going to do this, and it's still a rightward force being applied. I still have an F of G. I still have an F of N. I don't know why it says neglect air resistance. We didn't drop it. So this is F of A, but now since it's going to be a constant velocity, my F of A and my F of F have to be equal to each other because they have to cancel each other out. So you should kind of draw those about the same size. All right. Number 7, a college student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. So really we only have to talk about the bag itself. It has a weight of F of G, and it is going to be on his shoulder with one strap. So that strap is really like a rope or a cord. You could kind of say it that way. So you could either say it was F of A or F of T, either way. But that F of T has to balance out the F of G because it's not moving, it's motionless. So those have to be equal to each other. All right, a skydiver is descending with a constant velocity, number 8. Consider air resistance. Okay, here's our skydiver. He's a box. He's got downward weight, and he's going to have upward friction. Since it is a constant velocity, my F of G has to equal my F of F value. Number 9. A force is applied to the right to drag a sled across loosely packed snow with a rightward acceleration. So if we're doing a sled here and we're going to pull it to the right, it's an F of A, and I have an F of G, and I'm going to have an F of N, and I will have some frictional, if it's loosely packed snow, I'll have some frictional force, but it won't be as large as my F of A, because there is a rightward acceleration. Now, number 10, a football is moving upwards towards its peak after having been booted by the punter. Okay, well, the thing to realize is the football has weight. So we have our F of G. Now, it is moving upwards towards its peak, which means we have an applied force. So we could say it's an F of A value. And therefore, this F of A value, it's going to actually descend. But if you remember, we have components here. So that will cause it to go forward and up. So this F of AY will not equal this F of G, because as it goes up, remember, it's going to decelerate. So this F of AY will actually be bigger. F of AY will be bigger than the F of G because of that acceleration rate kind of going backwards. So that's something to realize, okay? But again, you don't have to actually draw the components. So really just even putting it at an angle, even though we weren't told it was at an angle, that's roughly what we can do. And then number 11, a car is coasting to the right and slowing down. Well, here's my car. And the car doesn't move up and down unless it's got, some major woofers going on and it's, bouncing because of the bass and all those kind of things. But nothing was talked about like that. So it's coasting. So actually, you don't even have an applied force going forward anymore. So with the gas information, so we just have a frictional force going backwards, and that will cause it to decelerate because it's actually moving back. It's going forward, but the force that was going forward actually was taken off. And so now as you have a frictional force being applied backwards, that's going to cause that acceleration to go in the opposite direction. So the opposite direction is actually slowing down. All right? So, the next part of your notes is Newton's law of universal gravitation. I am going to record that and put that on the website. So, for examples 1, the inverse square law question, example 2a, example 2b, those will all be covered on a separate recorded notes that I will have you guys listen to. I probably will not get to it until Monday though, so I'll have you guys listen to that maybe Monday night, and we'll go from there. Okay? You guys right now should be getting a worksheet where you're going to be doing some balanced forces. So I want you to really, and we're going to also be talking about mass and versus weight. So you'll be working on that worksheet. And remember, if they're balanced, then everything, all directions, up, down, left, and right, has to equal 0. But if I want a net force in a certain direction, then that means that I want that amount to be left over when I get done adding and subtracting all of the forces in that plane. So you guys work through that worksheet, and then I think you guys should be good to go. You're going to turn that in for the day, and tomorrow you guys are going to listen to another set of notes, and we will work on some more problems. Be good. Take care of business.